Hey everybody, Walt here for OverKill Projects. Today we're going to continue on with part 2 of our AN31 Amplifier Circuit Collection series by showing you how to make op-amps do your math homework. Kinda. Not really. Look, it's obvious that electronics can do a lot of really cool stuff, right? We have electric cars now. I have an electric piano that sounds damn close to an actual piano. I mean, there's not a lot that these things can't do. And last time, we showed that we can use op-amps to amplify tiny signals. And in fact, in the last video, we used that knowledge to amplify signals from a magnetic transducer that were really small into things that we could actually read with, say, like an Arduino or something like that. And now it's no shock that computers and electronics in general can do mathematics. I mean, obviously your calculator is electronic, it does math, right? What might be a little more surprising is that we can use electronic components and op-amps to make analog calculators. We can do analog mathematics with these things. And in fact, this is one of the fields of electronics that I find kind of the most fascinating. It was one of the first things that really just drew me into this entire topic as a whole. The idea that we can perform really complex analog mathematics, like really crazy with nothing more than an op-amp and some resistors and capacitors and all that sort of nonsense. Now, the idea that things in nature can just do analog mathematics is not very interesting in and of itself. I'm sitting here with a thing full of cherries like an idiot because, even with cherries, we can do analog mathematics really quickly. Look, I have 2 cherries. I have 3 cherries. I have 5 cherries. I just did analog mathematics with cherries. And now cherries are really good if you're adding or subtracting discrete quantities like 1 or 6 or even like 400 million maybe. If you had an entire grove of cherry trees. Are they called groves? But cherries are hardly useful if you're trying to solve a differential equation or approximate pi. Except for cherry pie. Oh, God. But it turns out op-amps can do all those things and a ton more, as we're going to see as we move through this circuit collection. And a lot of those things can be useful even in a largely digital world. Just because these things perform analog mathematics doesn't necessarily mean that you have to build some sort of analog, calculator. But sometimes it can be very useful to combine signals or find certain points in an incoming signal using analog mathematics that then get picked up by like a microcontroller or a processor or some other nonsense down the line. Now, when I say analog math, that's just to differentiate it from digital math, which is what your microcontrollers and microprocessors do. Microcontrollers and microprocessors take a binary representation of your numbers, that is, they're digital, and then they perform mathematics on those binary figures in some sort of sequence, and then they give you an answer. And now digital mathematics has become extremely good lately, right? Because we have, say, 64-bit processors, and a 64-bit number is massive. But this has not always been the case. Early computers were 8-bit or less, which gave you way fewer values, say, between 0 and 1. And not only that, but in a microcontroller or a microprocessor, mathematics is performed sequentially. So if I want to solve a differential equation, for instance, it could require maybe hundreds of steps to get that job done. And now when your modern controller can run at, 200 megahertz or modern processors into the gigahertz, that is a lot less of a bottleneck because those hundreds of computations are going to be performed in a fraction of an instant, really. And so you don't even notice that that work is being done, which isn't to say that we can't develop things that stress modern microcontrollers and microprocessors. It's just that it's relatively practical to do relatively complicated computations on even the most basic modern computers. However, again, that was not always the case. In the early days of computing, hundreds of calculations could require some amount of time. And if you were doing that over and over again, it could require quite a bit of time. However, analog computing allows us a way to get those same results almost instantly. Of course, the price you pay is that the calculator you build is much more specialized, it's much bigger, it's going to consume a lot more power. But in the era when this was one of the only ways to get the results you needed quickly, that really wasn't a problem. And in fact, that is why op amps are called what they're called, operational amplifiers. They are operational because they perform mathematical operations. They're also amplifiers, but as we're going to see in a second, amplification is also a mathematical operation. So really, they're little math machines, which is pretty stunning when you consider they are just sort of an agglomeration of a whole bunch of transistors that are burned onto a little piece of silicon and then shoved into a plastic container and then soldered down to something or other. They are by themselves as inert as cherries, but they can do so much more than cherries. It's pretty great. Now, all of this was a roundabout segue to get to what we're actually going to do today, which is build circuits that can add and subtract. Pretty slick. Turns out we've actually already done multiplication and division. That's just amplification. If you think about it, you'll realize that our inverting amplifier, for instance, took our incoming signal and multiplied that by some negative number, which was our gain. So specifically, the circuit that I built in that video multiplied our incoming signal by -10. In other words, we built a circuit that multiplies by -10. And the inverting amplifier we looked at multiplied incoming signals by a gain of 11, which is to say that we multiplied by a positive number. It's also worth noting that inverting is the same as multiplication by a negative number, so we already have a way to turn positive values negative, negative values positive, to multiply and divide. So now if we learn how to build circuits that can do addition and subtraction, we have everything we need to perform all the same operations as a 4-function calculator. That's pretty cool. So now we're going to take a look at the next 4 circuits in AN31. So those are circuits 3 through 6, I believe. And just a quick note that when I cover these, I am going to fly through the analysis part, not because it's not important, because it is important, but because I'm trying to keep the length of this video to a minimum, since YouTube seems to only like to recommend things between like 10 and 15 minutes. But YouTube has other functionality that kind of makes up for all that. You can slow it down and listen to it again and again. You can pause it when there's something you don't understand and take some notes and try to make sure that you can pick up what it is I'm saying. In short, what I'm saying is, if you don't understand what I'm saying the first time through, don't let that bother you. It is not easy stuff necessarily, and I'm moving very quickly. So take your time and go at your own pace, and don't let the speed at which I do the thing startle you. All right, that's enough with the disclaimers. Let's take a look at difference amplifiers. Difference amplifiers, or differential amplifiers, are just a generalization of our inverting op-amp configuration. And that should be no surprise. If you were paying attention when we were deriving the formula for the inverting amplifier, you'll notice that one of the things that we're looking at is the difference between the input voltage and ground. So we're already looking at a difference. And now the natural next step from the inverting amplifier would be the inverting amplifier where you bias the non-inverting input. And in fact, this is exactly what I did in the circuit that you might have seen in my homemade seismograph video, which is the last video. But once you introduce those new components, those 2 new resistors into this circuit, you sort of change things around. Now, I actually left a tagged comment on that seismograph video asking you to take a look at what difference the biasing voltage divider makes to that circuit, because it does in fact make a difference. And now in an inverting amplifier, you sort of are biasing the inverting input as well by using a resistor network of voltage divider between V out and V in. So it should feel natural that a generalization of that idea is to now bias the other input. And in fact, if you were just to sort of follow what you do on the inverting input with the ideas that you have from an inverting amplifier, you would probably try something like the circuit that you see in AN31. But now, how does this configuration actually work? I'm glad you asked. Let condition A be that V2 equals ground, or 0 volts. Actually, this could be anything, any sort of reference point, but for now, we'll just call it 0 volts, and you can go back and make sure that you understand that you can do this with any reference voltage. And now you should notice right away that since V2 equals ground, what we have here is exactly an inverting amplifier. And so our V out for condition A is going to be exactly the inverting amplifier equation, which is just negative R2 over R1 times V1, which is the same as saying that the gain is equal to negative R2 over R1. So now let's flip it around. Let condition B be that V1 equals ground. Then we have that the positive input is just part of the voltage divider that's formed by R3 and R4. So our equation is R4 over R3 plus R4 times V2. And since both of the inputs are the same, again, we have that the inverting input must be the same. But now since V1 was ground, we actually have a voltage divider again between V out and ground on the inverting input. And so we have another way that we can write the input voltage at the inverting input, which is just R1 over R2 plus R1 times V out under the B condition. So now rewriting that, we can solve for the B condition V out, and we end up with this equation. Now by the principle of superposition, we have that the total V out must just equal the A condition V out plus the B condition V out. So we just add up the two things that we got, and there you go. That is the equation that we see in App Note 31. But now if you look at this equation, you'll notice that it's not just subtraction. It's a bunch of things times V2 minus a bunch of things times V1. So what we really have here is a form of weighted subtraction. So suppose we wanted an actual subtraction to be in here. In order to do that, we would have to be able to factor out both of the coefficients, the coefficient of V2 and the coefficient of V1. In other words, if we rewrite the V out equation as A times V2 minus B times V1, we see that we would have to have that A equals B in order to factor out the coefficient. So let's figure out what that would take. We'll write A equals B. And now just some simple algebra shows us that we have to have that the ratios of the resistors should meet this criteria, that R1 over R2 is the same as R3 over R4. And now if we meet that condition, then we actually get the equation that you see at the bottom of figure 3 in App Note 31. However, you'll notice that we don't have the same condition that they do. They have that R1 has to equal R3 and R2 has to equal R4, where our condition was just an association between two different ratios. The reason for this is simply that we want to have impedance matching between the two inputs. We want V2 and V1 to see the same impedance when they come in. So now we have the condition we just came up with, as well as the condition that both of the inputs see the same impedance. And putting those two things together, we end up with R1 has to equal R3, R2 has to equal R4, just like the sheet says. And so now we're great, right? Wrong. It turns out that this setup has quite a few caveats, like a lot of caveats. So if you take a look at it, you'll realize that if you even have 1% resistors and they're off in the right configuration, that this thing can go pretty wrong pretty quickly, especially if you have a large amount of gain. And so not only is it critical that you match the resistor values with really high precision, but it also becomes very important that the input impedance from both of your sources, your source impedance, is the same. Even small variations in source impedance can cause this amplifier to work nothing like how you would want it to work. It turns out that this can create really big problems if you're trying to implement this circuit in the real world. Luckily, like with everything, there are some answers and some trade-offs. In order to solve the resistor matching problem, you can buy this configuration built into an IC with the resistors already built in for you. And now these ICs are built specially to have the resistor values be extremely precise so that you don't have to worry that there's some sort of mismatch or that even wiring it up might cause some sort of extra impedance that's going to throw your values off. So that's one problem out of the way. However, the source impedance problem is a little harder to get around. There is a natural fix for this, and that is to buffer the input from both of the sources. And now if you do that, you have what's called an instrumentation amplifier. And instrumentation amplifiers are themselves packaged in their own ICs, or you can build your own out of some op amps like we see here. But now we're going to run into that later because I'm pretty sure that instrumentation amplifier is in this circuit collection, and even if it isn't, I'm bound to make a video where I have to build one into something. They're actually pretty common devices. And so now that's circuit 3. Let's take a look at circuit 4, which is very closely related. It's a low power difference amplifier. And now you can see here that this configuration is nearly identical to the circuit we just looked at. The only real difference is that the resistor values are huge and there's two mysterious capacitors just sort of floating around on our circuit now. The idea of higher resistances should be obvious to you. We're looking for lower power, and so larger resistance means that we're going to get less current. Less current means less power, which means that we can power something like this from a tiny battery. But again, there are caveats. Even though this works identically to the previous configuration, if you try to set this up with the wrong kind of op amp, you're not going to get very good results. For this sort of configuration, it's pretty much mandatory that you look into using what's called a Cmos amplifier. Remember that if you look into the internals of an op amp, you're going to see at least the equivalent of a whole bunch of transistors flowing all the way through from the input to the output. In a Cmos amplifier, the input stage transistors are MOSFETs. And something you should know if you haven't looked into discrete components like MOSFETs and BJT and JFET transistors is that MOSFETs have extremely high gate impedance. By having huge input impedances compared to the resistor values, we ensure that these formulas are going to remain relatively valid. And in fact, we have resistors in this configuration that are on the order of 10 to the 7th or so. So if we have an input impedance of around 10 to the 13th, that guarantees us something like this. Something like 6 orders of magnitude worth of precision before we have to worry about the influence that these resistors have with the input impedance. Which is something like saying that we're 6 orders of magnitude closer to an ideal op amp. But now, what about the capacitors in this configuration? What's that all about? Well now, since this is a low power device, we might be looking at relatively small input signals. And if we're looking at small input signals, there's a chance that our input signals might start to get muddled around with the noise that is also occurring on the inputs. And now in order to isolate our input signal from the noise coming into the op amp, we build ourselves a low pass filter into the feedback loop so that we don't have to worry about high frequency noise from something like a microcontroller that might be nearby, infesting our input signal and making it very unreliable. And now I'm not going to go into the nitty gritty of how a filter like this works right now. In fact, I think we might see it in an upcoming video. But they give you here the equation for just exactly what your cutoff frequency is going to be. So if you know, for example, that your input signal is going to top out at something like, I don't know, 2 kilohertz, then you can build this filter to filter out anything over maybe 10 kilohertz. That way you don't have to worry about that noise. And C1 in this configuration does exactly the same thing, but with our VIN2 signal. It also is working to filter out the noise, but from that input signal. And now something to keep in mind is that really you should make C1 and C2 the same value. So you need to take the larger of the two possible frequencies from VIN1 and VIN2 and create your filter based on that value.
Another good reason to add these roll-off capacitors is that large resistors tend to have very high inductance, which can cause a circuit to misbehave, especially at higher frequencies. By rolling off your signal frequencies in a controlled way, you avoid some of this inductance.
Okay, let's take a look now at the summing amplifier. The two summing amplifiers are two of the easiest circuits that we're going to see, assuming that you understand our inverting and non-inverting amplifiers. The inverting summing amplifier from figure 5 is just an inverting amplifier with a whole bunch of different signals coming into the inverting input. Now I'm going to let you do the analysis on that because it's the analysis that we've already done for inverting op amps. The only difference is that now the incoming voltage is 3 parallel voltages. And so now since those 3 input signals are all in parallel, it shouldn't be any surprise that in the formula we see that all 3 input currents are added up. It's nearly identical to the way that you would figure out how parallel resistors work by adding up all the currents. Then you just rewrite the currents as voltages divided by resistances, and you'll end up getting this. You'll also notice in this configuration that they have R5, which is the optional input bias current compensation resistor, which is particularly handy if your op amp has a high input bias current, especially if you have something like a BJT op amp. And now I talked briefly about this resistor in part 1 of this series, but it's sufficient to say that what you're trying to do here is you want the non-inverting input to see the same impedance as the inverting input. And so if you calculate what that value would be at the inverting input, which would be the parallel values across R1, R2, and R3, paralleled with R4, you would get roughly 250, actually exactly maybe 250 ohms. And now the same exact thing with the non-inverting summing amplifier. If you just look back to part 1 of this, in case you forgot how to derive the formula for a non-inverting amplifier, it's the exact same thing, but now we have 2 voltages coming in parallel. So again, you're going to parallel them together. You have 2 currents coming in now instead of 1. And then when you solve everything out, you're going to get the equation that you see right there. So I'm going to go ahead and let you do that, because honestly, you should sit down and try to figure out some of these from time to time to make sure that your math for electronics, for this sort of thing in particular, is sharp. It's a good skill to have. All right, that's enough analysis. Now I'm going to go build a couple of these onto a breadboard, and we can just take a quick peek at their performance.
You can see here the differential amplifier laid out on a breadboard. This is exactly the same circuit that you see in figure 3. I went with a TL071 op amp, which is a JFET input op amp. Like I mentioned before, I went with this because the JFETs on the input give this op amp a relatively high input resistance, in this case around 10 to the 12 ohms, which is on the order of tera ohms. This op amp also features incredibly low input offset current and input bias current for an op amp in its price range, as well as a relatively low input offset voltage. And I expect that we're going to see pretty great performance out of this op amp. It's actually a pretty good op amp if you're going to hand make your own differential amplifier configuration like this, and really a pretty good op amp overall depending on your needs. The only real exceptions being that it doesn't have the highest bandwidth available, and it also requires enough supply current that if you are trying to power a device from, say, a coin cell battery, you could probably do a little bit better. But again, this should be a pretty good performer, so let's hook it up and see what we get. Here is our setup to test out DC voltage. You can see that on the power supply, I have it configured in series at 18 volts, which means that I'm getting 2 supply rails, a plus and a minus 9 volt supply rail, as well as a ground rail. The third output of the power supply here, I'm actually going to use for our V1, which is our inverting terminal voltage input. And for V2, I'm going to use the 5 volt rail from an Arduino. Now, of course, the Arduino says it's a 5 volt rail, but I don't expect that to be dead on. So we will measure the input from that first, and then we'll try to get it pretty close from the power supply and see if we don't get 0. We'll just try out something else too. And up top you see the multimeter. It's a 5.5 digit multimeter. I'm going to use that to measure both of the inputs and the output and sort of make sure that, you know, we're getting what we expect to get. So first up here is the voltage from the Arduino. You can see that it's in the neighborhood of 22-ish millivolts above the 5 volts that it claims to be. And so I'm going to set the output from the power supply to be roughly the same. So I'll just set that at 5.022 volts. And measuring that, we see right around 5.022, 217 volts. And now checking the output, we expect it to be about a 1 millivolt negative, which it is. And that's because in our difference amplifier formula, we see that we get V2 minus V1. Here we know that V2 is just a little bit less than V1, so we're getting almost exactly what we expect to see. Although it's worth noting that almost exact is not exact. In this case, based on what we were seeing before, I think we would expect something like negative 4 to 600 microvolts, somewhere in that neighborhood. And so it looks like we might be off by something like 600 microvolts, give or take, which in this case would mean that we're off by around 0.1%. And now, obviously, for some applications, 0.1% is perfectly fine, but there are plenty of times that you would want a lot more precision than even this. So for example, if you were looking for precision down into the parts per million, then you would be looking for something on the order of around 1/10,000th of 1% or better. And now this is actually performing relatively well considering we're using 1% resistors here. And of course, we could bump that up to 0.1% or 0.100% resistors, but there'd really be no point. The cost curve at that point would start to get ridiculous, and it would be much more effective just to use a differential amplifier IC at that point than to try to balance this out perfectly with external passive components like better resistors. And really, if you had to do this with external components, you'd be way better off using like a 25 turn pot or something like that and really zeroing in on the values that you need. So now I'm going to set our V1 to a different value and see that yes, we do indeed keep getting what we expect to get. In this case, I'm just going to set our power supply to 3 volts less than I measured on the Arduino power supply, and then make sure that we get 3 volts out on the multimeter. So dialing that in, we see that we get relatively close. We appear to be within a couple of millivolts of what we expected to get. And now just changing the output for the power supply a little bit, we end up getting our 3 volts. But that's actually something else that you need to consider when choosing op amps for this application, is that you want an op amp that's going to have extremely linear performance, especially in the range that you plan on measuring. Okay, looking at DC voltages is fun and all, but I think that this circuit gets a lot more interesting when we look at AC signals on the input and start subtracting one function from another function. So I'm going to hook this up to the 2 inputs of my function generator, and we'll take a look at the outputs on the oscilloscope. Here I have the oscilloscope set up with both of the input channels and the output channel. On the screen, we have from the bottom to the top, the yellow signal is channel 1, which is V in 1. The pink channel, the middle one, is channel 2, which is V in 2. And the top, the blue channel, is channel 3, which is our V out. You can see over there on the right that they're all 1 volt per division right now. And I am triggering on the bottom one on V in 1 just because it seemed like a good choice. So now I'm going to go ahead and turn on the function generator. Both inputs are going to be 1 kilohertz, 1 volt peak to peak sine waves. And so we should see 0 on the output. And that is exactly what we see. Even zooming in, we see that we get a really nice looking relatively 0 curve here. There's some noise as you could zoom all the way into 10 millivolts per division, but a lot of that's just going to be stray inductance from the loops that are created by the ground wires on the probes. And to get an idea of how this looks on the output, I'm just going to turn on some of the measurements, the peak to peak, the max, and the frequency for that signal. We can see that all the numbers are relatively low, especially for something on a breadboard with a bunch of stray wires floating everywhere. If there was some sort of difference being picked up by the amplifier, we would see that as a 1 kilohertz frequency, and it's not picking that up, which means that at the very least it's below the threshold for this oscilloscope to see it. Although admittedly, I do think that when you're zoomed all the way in, you can kind of see that there's a little bit of wave on the output, but it's pretty minimal here. You would need a much better setup to actually see what sort of difference there was here. But again, that's to be expected. The resistors don't match each other perfectly, so we expect there to be a little bit of error here. And the fact that it's actually buried down in the noise under everything else is a pretty good sign that everything was pretty well matched when we hooked this up. Alright, now I'm going to adjust the phase on V in 2, which is channel 2, the middle one, the pink one, and we will see the appropriate response on the output. We expect to see, sine of t plus some phase shift minus just sine of t. Now there's like a million different ways to represent that, but what we expect to see on the output is another sine wave that will be itself shifted in phase from the other two, and also with a different amplitude. At first the amplitude, like it is right here, is 0, and then that will grow up until the point where we have V2 is 180 degrees out of phase with V1, when we should get an amplitude of 2 volts peak to peak, which of course is what we expect, because a sine wave at 180 degrees phase offset is the same as negative sine, and so negative sine minus sine is the same as negative 2 sine. So we should see a negative sine wave with amplitude 2, which is to say that it'll have a negative slope of 2 going through 0. But let's check it out, we'll see it. And now here we are shifting V in 2 by 10 degrees at a time. And I'll stop here briefly at 60 degrees just to make note that the output is a 1 volt peak to peak sine wave with a phase shift of 120 degrees. So this is like looking at a 3-phase AC power line or something like that. And now we continue to shift the signal on V in 2 until we get to 180 degrees, and sure enough we see that the output is 2 volts peak to peak. We see that it slopes downward as it goes through 0, which is like in the middle of the screen there. It's exactly what we expect to see, and if we keep going, of course we can go all the way up to 360 degrees, and that's just the same as going back down to 0. Okay, so pretty cool, right? But what can you do with it? Well, there are a lot of reasons that you might want to take a difference between two different sine waves like we have in this case. So for instance, just right off the top of my head, Well, clearly you can use this to determine phase offset. If you have two incoming sine waves and you know what their amplitudes are, then you can measure the amplitude, the peak-to-peak voltage on the output, and use that to determine what the phase offset must have been between the two incoming signals. And so this is one of the many ways that if you're looking at the power used by an AC circuit, you can figure out the difference between, apparent power or active power or reactive power, and determine what the power rating of your device is. And just to give you an idea of how well this sort of thing performs, let's just take a look at a couple of the waveforms, and you'll see that this thing performs sort of exactly how you would imagine it would, or how you'd want it to. So if we change channel 2 to a square wave, we see that we get a square wave minus a sine wave on the output. And again, we can shift and change all sorts of the parameters for that, and we'll see that it behaves exactly like you would imagine it would. And we can even perform more esoteric mathematics. We can do, like in this case, let me dial it in. We have a parabola on channel 1 and we have a cubic function on channel 2, and so channel 3 is a polynomial, x cubed minus x squared. And now this is an interesting thing that we have here, is now that we are capable of making circuits with arbitrary gain, and we have a differential amplifier, which means we also have summing amplifiers. Now we can take our incoming voltage and actually transform that into any arbitrary polynomial. So if you had some reason to model something with voltage according to any arbitrary polynomial equation, you could do that. Why you might want to do all that is up to you, but one of the nice things that you have available to you now in the toolbox is that if you have a model that's based on some polynomial function of an input value, you can actually go ahead and build an analog circuit that will produce that model on its output. And obviously from there you could read it into a microcontroller or something like that. But you could also take a portion of that output and feed it back into the input, and you've got yourself this polynomial feedback model. And now eventually down the line, I'm going to use that to build a circuit that will do a little bit of science for us, which should be kind of neat to see. But I highly recommend taking something like this circuit, building it out, and sort of fiddling around, seeing if you can't devise some way to look at something that would make a model like this useful. And it really is kind of enlightening to build out something like this and in fact do that, build a feedback circuit where some of the output goes back to the input and then gets remodeled into the output again. If you've ever dealt with recursive functions, this actually gives you a way to electronically model continuous recursion, which is an entire field in and of itself in differential equations, especially delayed differential equations and stuff like that. But it's pretty fun stuff to check out. But that's a different topic for another day.
And there you have it, a quick look at summing and difference amplifiers. Maybe they can't quite do your math homework for you. I might have overpromised there, but they're still pretty darn neat and extremely useful when you're actually building electronic circuits, so they're a good thing to have in the toolbox. I hope you had fun and learned a little something today. I know I certainly did. And if you did, please hit me with a thumbs up down below. And make sure you subscribe and hit the alerts button so that you don't miss any new content. All right, that's going to do us for today. I had a great time. Thanks for joining me, and I'll see you next time.